Our Lesson 94 assignment was to create a binary counter that would count up when the red button was pressed and reset when the green button was pressed. Paul reminded us that the wait command, being a blocking command, is of little use with multiple inputs because while we're waiting for the status of one input to change, we'll miss any activity on the other inputs. Paul suggested that we could determine which button was pressed by examining the on-off pattern of the input pins. PIO assembler comparisons are done between X and Y scratch registers, so we need to get the button status into one of those registers. We'll start by using the in command to shift n of the least significant bits from the input pins into the least significant n positions of the ISR register. Then we'll move the ISR contents into the Y scratch register for comparison. Here's the code. As usual, we start with imports. We import pin because we use the pin statement in the PIO instantiation. We import RP2 because we're going to be programming a state machine. The RP2 decorator on line 7 specifies that we'll be using out instead of set, and we'll start by setting our 4 outputs low and setting the shift direction parameter to right. Because the up reset counter function definition follows the @RP2 decorator, it will be interpreted as assembler code, not MicroPython code. The up reset counter function contains the assembler code for our counter. We'll return to that shortly. Here we define our two push buttons by specifying the GPIO pin number, the data direction, and enabling the pull down resistors for each one. Line 42 instantiates state machine 0 by specifying the state machine number, the name of the function containing the assembler code, the least significant GPIO input pin, the operating frequency, and the least significant GPIO output pin. Line 43 activates the state machine. The remainder of the program is a try except clause containing an empty while true loop and a Control-C exception which will deactivate the state machine and message the user that the program has stopped. The up reset counter function, which starts on line 9, uses the invert decrement invert method of adding. If you're unclear about how this works, you can find a complete explanation in my Lesson 90 homework. There's a link in the description below this video. Main sections of the program are identified with label statements. The assembler code starts with the label start statement on line 10. We set the 4 least significant bits of the X scratch register to binary 0, then copy that value to the OSR. The show label on line 14 marks the part of the code which copies the contents of the OSR to the output pins. On the first pass through the program, this will display 0000. Every time execution jumps to show, the LED pattern will be updated with the current contents of the OSR. The read button section of the program starts by copying null to the ISR register to clear out any previous data. Recall that we defined our in base as red push button in line 42. This means that red push button is the least significant bit of our inputs, and green push button is the next significant bit. The in instruction on line 19 shifts those two least significant bits from the input pins into the least significant bit positions of the ISR. We throw away 64 cycles in order to debounce the switches, then copy the ISR contents to the Y scratch register. Now that our push button status is in the Y register, we can use comparison statements to determine which button was pushed. The red and green push buttons can only generate a small number of combinations, as shown here. So one of those patterns must now be stored in the Y scratch register. Comparison instructions will help us determine which one. We'll start by checking if nothing was pushed, i.e. the pattern is 0000. We load binary 0000 into the X scratch register in line 25. This is the pattern for nothing was pushed. If nothing was pushed, the Y register will also contain 0000, so the jump in line 26 will not execute. Execution will fall through to line 27, causing a jump back to the read buttons label, and the program will capture button status again. On the other hand, if one or more of the buttons were pushed, the Y register will not contain binary 0, and line 26 will execute, moving program execution to the Are We Incrementing label in line 29. In the Are We Incrementing section of the program, we test if the red button was pushed by comparing the Y scratch register to binary 1. If the green button or both buttons were pushed, the Y register will not contain binary 1. Line 31 will send execution back to the start of the program, the counter will reset, and the whole process will repeat itself. On the other hand, if the red button was pushed, execution will fall through to line 32, where the program will wait for the input pin, which is offset by 0 from the in-base pin, in other words, the red button, to be released. Once the red button is released, the program copies the inverse of the OSR to the X register, decrements X if it's greater than 0 in line 34, then copies the inverse of the X register back to the OSR. This is the invert, decrement, invert method of adding, described in lesson 90. Execution then jumps back to the show label, where the updated count is displayed and the process repeats itself. And here's how it works. Well, that's it for this assignment. Any and all comments are welcome. Don't forget to like or dislike the video before you go. And feel free to subscribe. Don't forget the notification bell. We'll talk to you next time.